4B. Operations with vectors. Geometric techniques. When more than one quantity is involved in a problem, vectors often need to be added, subtracted, or multiplied. They may be multiplied and divided by scalars as well. Mathematicians have developed methods to simplify these operations and yield useful results. The geometric techniques of vector math can be done quickly with only a ruler and a pencil. 4.4. Adding equal vectors by scalar multiplication. The simplest case of vector addition is adding a vector equal to itself. Graphically, this is accomplished by placing the tail of the second vector at the tip of the first. Their sum is the vector drawn from the tail of the first vector to the tip of the second. The vector sum, called the resultant, is twice as long as the original vector and is oriented in the same direction. V plus V = 2V. The bold plus sign indicates vector addition. Note that this vector sum is also the product of a scalar number and the original vector. When a vector is multiplied by a positive scalar number, its length, magnitude, changes, but its direction stays the same. The magnitude of a vector 2v is 2v. In figure 4-12, if this a vector 6 units long, 2v would be a vector 12 units long, pointing in the same direction as v. If the scalar multiplier is negative, the resulting vector points in the opposite direction from the original. Thus, v, that is, 1xv, is a vector 6 units long, pointing in the opposite direction from v. Scalar coefficients may also be fractions. So, 1, 2v, or v2, is a vector 3 units long oriented opposite to v. 4.5. Adding unequal vectors. Graphically, how are two different vectors added, for example? A plus b. If they have different magnitudes but the same direction, then their resultant r is a vector whose magnitude is r ℏ a plus b, and it has the same direction as the original vectors. Again, the resultant vector extends from the tail of the first vector to the tip of the second. Observe that there is no difference in the resultant r between the operations a plus b and b plus a, see figure 4-13. In other words, vector addition is commutative. In most physics problems, however, vectors are usually unequal. They don't have the same magnitude and rarely point in the same direction. Let's look at a two-dimensional example. A student pilot flies 30 kilometers north and then 40 kilometers west on her solo flight, shown in figure 4-14. The two flight legs are displacements that it can be represented by vectors. To find the plane's net displacement from the airfield at the end of the second leg, you must sum the two leg vectors. Using the graphical method, each leg is drawn to scale on a sheet of paper or a map. Since vectors can be transported without changing their magnitude or direction, you can place the vectors head to tail in either order. As before, the sum of the two vectors is the resultant vector that stretches from the tail of one vector to the tip of the other. The resultant is identical to the path the aircraft could have taken to fly directly from the airport to its position at the end of the second leg. You can find the magnitude of the resultant displacement vector graphically by measuring its length with a ruler and applying the map's scale factor. The airplane is found to be 50 kilometers from the airfield. Notice that this is not the arithmetic sum of 30 kilometers and 40 kilometers. When the directions of the vectors are not identical, the magnitude of the resultant is not equal to the sum of the magnitudes of the two legs. R is not A plus B. The direction of the resultant is also different from either of the original vectors. You can measure the compass direction, vector angle, from the airport using a protractor. Measured clockwise from north using navigational angles, the error aft bears 307 t from the airport. Now, note that when the resultant must be measured from a diagram, each vector must be drawn accurately to scale. 3 or more vectors may be added in a similar way. Place the tail of each vector of the tip of the previous one. Their resultant is the vector drawn from the tail of the first to the tip of the last. Because vector addition is commutative, the order of the vectors does not matter. 4.6 Vector subtraction. In the expression AB, the bold negative sign indicates vector subtraction. Recall from algebra that subtraction is equivalent to adding the opposite of a number. Subtracting 3 is the same as adding 3. The vector expressions AB and A plus B are equivalent. Remember that a vector's opposite has the same length, but points in the opposite direction. Once you have found the opposite vector, vector addition is carried out to find the resultant. Note that, as with arithmetic subtraction, vector subtraction is not commutative. That is, AB is not the same as BA. See Figure 418. A second method exists for easily finding the graphical difference of two vectors. Place the two vectors tail to tail. Then draw the resultant vector from the tip of the second vector in the difference equation to the tip of the first. A difference vector, e.g. delta v, is the resultant of a vector subtraction operation. See example 4 to 2. This method is useful for determining the change in a vector quantity. We saw a difference vector in Chapter 3 when we determined average acceleration, where a bar is delta v over delta t. In this case, delta v is the difference vector of the velocity measured at two different times.